Alright, if you're watching this video, you need to go back and read the notes on the first 2 slides. Okay, so if you want this, you gotta do E cell, which is E red minus E ox. Quick reminder though, when I talk about reduction minus oxidation, I'm talking about the electrodes or the ions that are undergoing reduction or oxidation. These are still called what potentials? Reduction potentials. You would still get them from the reduction potential list, which is the list you have, or there's a list in your book. How are reduction potentials, reduction half reactions written? Where are the electrons?
On the left.
In the reactant side. If you're reduced, the electrons are in the reactants. So that's what this all this right here on the board means. I know that a lot of us want to flip signs for some reason. I'm not quite sure, but E cell is cathode minus anode, or reduction reaction minus oxidation reaction. This minus here accounts for the fact that the second one is technically not a reduction half reaction, right? Both of these are oxidation half reactions. So this negative sign here accounts for that. So sometimes, like, I think in physics you see it this way more often. I prefer you stick with one and stick with it for the rest of your life. You will never mess yourself up, okay? I've always used this one. If you ever see something like this, what it's referring to is the reduction potential of the reduction reaction plus the oxidation potential of the oxidation reaction. How do I get to the oxidation potential? Flip the sign. Guess what? When I flip the sign, it's probably going to be listed as positive, and it's probably going to be listed as negative, because most oxidations are going to be negative. This negative here, when this negative combines with this positive, what happens? It becomes overall a negative, which is exactly what this is. Okay, so these are all exactly the same equation, it's just writing the signs appropriately. I prefer you to use this one, just so this we can all be on the same page, but sometimes you'll see it like this. Alright, back here. Who's red? Who's reduced? I don't know. Why is it written like this? Anode to cathode. Okay, so is it like this or the opposite? It's like this, right? Reduction means you're gaining electrons. The other one, the zinc, is like this. Okay, cool. We're on the same page. So the reduction half reaction gives you a number such as, okay, hold on. This is 0.34 volts, and this one is negative 0.76. Okay, I wrote those down. So when I do this, I'm going to do 0.34 volts minus a minus 0.76 volts, which gives me 1.10 volts. That's one we see a lot between zinc and copper, so sometimes you might just accidentally grab that. Alright, so that's spontaneous or not? Spontaneous. What's another word up there that would automatically tell you that? Galvanic. Thank you. You should see those keywords. Okay, what do I do with this?
Times it by the number of moles of electrons, which is 2.
So delta G is equal to negative NFE. Okay, so what's the number of moles of electrons? How do you know that?
Yeah.
Alright, this one's easy because there's 2 lost and 2 gained. There's no balancing needed. Zinc loses 2, copper gains 2. Cool. F is what?
96,500.
96,500. I like to keep it simple if we can. Coulombs for moles of electrons, and E cell 1.10 volts. Alright.
I converted to kilojoules, negative 212.3.
Thank you. So before you convert the kilojoules though, it's negative 212,300 coulomb volts. And then what do you do? Yeah, so 1 coulomb volt is equal to 1 joule. So negative 21300 joules. Did I do that right?
No.
I missed a number. Okay, there we go. Negative 212,300 joules, which is negative 2.3 kilojoules for the delta G. And that yet again verifies that our reaction is spontaneous because it yields a negative value, and a very negative value. Yeah.
So the 2 moles of electrons is based on either one of them, or?
It's on the net change. So you need to balance it. In this case, it's already balanced because it was 2 and 2, but you need to do the balancing before you can plug it into N. Next one, ready? Yeah.
If the E cell goes up, wouldn't the voltage go drastically down?
Get more spontaneous, right? It becomes a bit larger magnitude, but you still have to count for the sign, whichever way it is.
But like, I mean, because you said they're directly correlated, but doesn't like voltage effectively get
It gets more negative, right?
Yeah.
More negative means that the negative value is a higher magnitude. So that the magnitude, that's where, like, if you're talking about pH and stuff, you gotta be very clear on what you're talking about. This one, you would say, as E cell goes up, the spontaneity of the reaction increases due to the larger magnitude of delta G. The magnitude is still, I mean, the sign is still negative, but still got a large magnitude. Make sense? All right, so using our logic, first, before we do calculations, logically, we know that, oops, no, not this one, sorry. Oops, not this one either. Oh, gosh. I didn't save this because it was first I didn't save it right. Okay, anyway. That's not what I want to do either. I'm going to go back. I'm just going to give you an example.
I can tell you the order of the slide.
I got the order. You got it right here. Oh, no. Let's just do this one. All right, using this half reaction set up already, we've got this one and this one. When you write the overall reaction, you get what? Overall reaction. Cu2 plus zinc yields. Okay. Logically, right now, if I increase the concentration of copper 2, what would happen to E cell? Shift. Okay, that's telling me what happens to the reaction. And then, so if it increases copper 2, shift right, and increase the electromotive force because you're forcing the forward reaction to occur more often, which means you're forcing the electrons to move towards the cathode more often with a higher force. I see confused faces. Are we okay with that?
Can you repeat that?
Yeah. So, how can I write this? Increase concentration of copper 2, according to Leschatz, will shift right. Increase it, shifts right. Okay? So, this way, the driving force of the forward reaction also increases because I'm shifting right. I'm increasing the force of the forward reaction. I'm increasing the likelihood of the forward reaction. If I'm increasing the likelihood of the forward reaction, there are going to be more electrons traveling from anode to cathode. More electrons, maybe at a higher speed. If there's more electrons traveling per time, what should happen to my voltage? Increase the voltage. So forward reaction favored, increase the voltage due to more electrons per time, which is in fact an increase in E cell. Related to it because that's what voltage is, yeah.
You just think of it as, since it's right, that makes it more spontaneous.
It would, you would probably say maybe not more spontaneous, but more spontaneous in the forward direction. But it's more about you talking about the electron flow or the electromotive force than the delta G. It's just related because E cell is directly related to the electrons flowing, so I think that's a better way to explain it. But they could give you credit. Like there's specific things on the rubric on the AP exam they would be looking for. Yeah.
So if you're increasing electrons, so then the difference between the anode and cathode increases, that's why your E cell is bigger?
The difference in concentration between the anode and cathode has a higher difference. They're still the same anode and same cathode, but now the concentration has something to do with it. So this whole time before today, we've dealt with 1 molar solutions, and you simply take E, cathode minus anode, we're done. But now that if I change the concentrations, there's 2 forces. There's just the simple difference between the anode and cathode, and the concentration differences, and that's going to either make the E cell increase more than it would likely be, or decrease more than what it would likely be. What it would likely be is this right here, at standard conditions. All right, we're going to talk about that, called the Nernst equation now. I always call it the Nernst equation. Forgive me. I don't like to say the other N for some reason. Okay, here's the Nernst equation. I think I put some of this in your guided notes. If not, take a couple minutes to write it down, and then I'm going to tell you how I derive it. Just so that you're not listening and writing, because this one's one that you're going to have to remember. It's not on your reference sheet anymore. It used to be. I'll give you just a minute or so to write that in the equations down. Start here and write down, just so I can show you how to derive it from something you know. Alright, stop wherever you are. I'm going to start at the top, okay? Give me a second, wherever you're ready. Alright, so this first equation is simply saying that normally the spontaneity of a reaction, delta G, at standard conditions is whatever this delta G number is. But if I switch up the temperature or the concentration of stuff, the spontaneity or the likelihood of the reaction can change. What does this Q right here remind you of again? Initial conditions of the product's concentration over the reactant concentration. What are the only things you can put into K or Q? Aqueous or gases, but we're dealing with mostly electrochem stuff, which is mainly aqueous solutions. No solids at all. So no solid electrodes at all. Okay, so I can either change delta G in a positive or negative way. If this is going to be shifting, if these conditions cause me to shift right, what should happen to the delta G? It's going to increase the magnitude because it's more likely to occur, but if it's a negative number, then we'll get more negative.
Yeah.
You see? Okay, I see some faces, but if this number, if I want to shift right, I get more, the E cell gets larger. It's more likely to proceed in the forward direction. It's more spontaneous. Larger G values, larger magnitude of the G value means that it's going to happen more frequently or more likely. But most of the time, if it's spontaneous, the delta G is negative, so it gets to be a lower negative number. I can go over that more. But if it's less likely to occur in the forward direction, the magnitude of the G gets smaller. So it actually gets more positive. Agree to disagree with me. It's a number like negatives, positives. It gets more positive if it gets a smaller magnitude. Okay, we'll come back to that. Okay. So, what'd you say? If you know if you know it's a negative sign, then yes. But if you don't know, then you don't know.
So what's the plus?
You have to know if it's a negative or positive to say if it's directly or indirectly. But I was thinking about the magnitude and then I put a sign on it. Alright, I'm coming back to that though. Alright, so pretty much what I'm trying to get you to see is that you can use your normal spontaneous number that you get, compare what happened to your cell, and then that's going to change the spontaneity of the reaction. But I don't really do a whole lot with delta G's, so I don't measure delta G's very well. I can only measure delta G's if I have the E cells. Alright, so we know that delta G is equal to negative NFE, standard conditions or non-standard conditions. So it can be delta G, no standard is equal to negative NFE, no standard. So what I did here was my delta G is equal to negative NFE. My delta G standard is equal to negative NFE standard. All I did was sub it in. You see that? Alright. So then this looks really complicated. Like I don't want to memorize that. How do you simplify? You see that you have negative NFE on left and right. Divide by negative NFE all the way. So, I'm sorry, not NFE, just NF. So if you divide by negative NF here, and then divide by negative NF on the right side, this is going to apply to this and this. I'm going to write it two places here just to show you. What cancels over here? Negative NF. Leaves you with E, right there. This negative N and F, oops, F, cancel, leaves you with E naught, which is right there. And this negative gets applied here in front of the R. So this leaves you with this funky constant. negative RT over NF. Negative RT over NF actually has values applied to it. The only one that's an unknown right now is which of these? The N. It depends on whatever the reaction is. Most of the time, if they change concentrations, they're going to keep the temperature at 25 degrees C because you guys don't need to know all the complicated stuff. The R value here, since we're dealing with volts are related to joules, yeah? So what R value do I have to use? 8.314 joules per moles Kelvin. That should make sense because you have joules, you have Kelvin, and you have moles of stuff, whatever it is. The T here is most likely going to be 298 Kelvin, almost exclusively 99.999% of the time. The F is always what? 96,500 coulombs per mole K. Per moles electrons. So I know this value, and this value. I don't want to write all that mess out. I'm just going to simplify it in a version that makes, it's just a number, it's a constant that makes more sense to me. So all I did was plug it in here. I'm showing you my products of reactants here. And instead of writing this big mess out, this right here is the Nernst equation. I'm going to write it in the simplified version. E is equal to E naught cell, minus all those variables put together, which is 0.0592 divided by N log of K, or Q. Could be K, but it's Q right now. Yeah.
How did it switch from
Because it's like a mathematical, whenever you have this number here, I can't remember what it is when you use the natural log base, but when you change it to log base, it's this number. And I think this number is easier to remember, and they use this in the textbooks all the time. So when you switch from natural to log, mathematically something happens, but I can't tell you that right now. I have to look it up. It's just, this was what they used to put on your reference sheet, and so we use that one exclusively, that version of it. Okay, so if I were you, I would remember this equation. E not standard is equal to E standard minus 0.0592 over N log of Q. You write it enough, you will memorize it. Okay, this is simply for calculations though. If you're trying to calculate the new E cell at non-standard conditions. Okay? Alright, now what if you have a dead battery? This is the only other thing you really got to know from this slide. If you have a dead battery, the reaction's not going anymore. Electrons are not flowing. At that point, that means the forward reaction and the reverse reaction are kind of equal, so we're at equilibrium. At that point, E cell, not E standard, just simply E cell, is 0. That one right there. That's because at these non-standard conditions, it's not going to happen. It's 0. It's dead. What else is true at equilibrium? Delta G is equal to 0, but Q is equal to K. All right, so I'm just putting these two things here because I want to set them in there to show you what the equilibrium one looks like. So at equilibrium, that E cell, this one, is 0. So let's rearrange that equation to show what it would look like at equilibrium. What can I do? E naught cell minus 0.0592 over N. Okay, I don't like that 0 there. How do I get rid of it?
Just E cell.
So just move this over here, right? So E cell, E naught cell is equal to 0.0592. Not negative, the negative's gone when I move it to the other side. Ln of K, log of K. So if I want to know the equilibrium constant, and I know E cell, and I know moles of electrons transferred, I can calculate the equilibrium constant. That's what Nathan did in 1988 problem. This is just a derived version of this though. So you don't have to memorize that. You mainly need to know that E cell is 0 at equilibrium. Yes. Sorry. Questions? Yeah. Why what?
Why wouldn't it be divided by log like 0.09?
Because this is an entity that stays together.
The whole thing.
Because it's multiplied by one another, so you can't separate them.
Okay.
So you want to keep them together. Thanks, Tristan. All right, can I go next page? Couple practice problems, okay, guys? All right, and I think I put this is the one I put on your sheet. This is what I was thinking for earlier. I can't find it. Alright, so here's my reaction. I think this E cell is 110. I didn't write it down, don't worry about it. Okay, so looking at this reaction, it's voltaic, it's spontaneous in the forward direction. Using your logic in Le Chatelier's, what's going to happen if C2 plus is increased?
Increase.
Give me the verbiage that you would say on the AP exam. Tell me the big 2 cents explanation you would tell the AP examiners.
Increase rate.
Uh-huh. Shift right, or so disequilibrium, I like that. So there's disequilibria, and causes it to shift right. Oh, hold on, therefore is not triangle, therefore is 3 dots. Therefore, force of reaction, of the forward reaction, would increase, causes, okay, I want to say increase in electromotive force, which is an increase in voltage, which is an increase in E cell. A lot of stuff. And that's all variable based, I'm sorry, but on the AP exam, they'll take some abbreviations like shift right probably, or reaction RXN, but other stuff you would have to kind of write out a couple more words than you would normally write out. Which one? They take therefore?
Yeah, because they did not make calculus.
I'll have to ask one of my guys who I know who grades stuff, because I'm not a grader yet, but I'm going to study, yeah.
That on the AP exam, if it doesn't specify that you're supposed to write your states, you're not supposed to do it because they take off points.
You write your states. Oh, for
If
NIEs?
you get it wrong, they'll take off points, and if you don't put it, they just won't.
Yeah, for NIEs, if you ever have to write an NIE and you're not sure about a state, I would write any of my states, like solid, liquid, gas, aqueous. But if you're definite or they need to know something, like you know it's solid, like something's conductive or a precipitate, if you know you're trying to form a precipitate, I would put PBT or down arrow or solid. Yeah, like if you don't know for sure, I wouldn't write it because that can change up for you for points. Yeah.
And if you put your states for one of the elements, we get states for all of them.
'Cause if you don't know them, I wouldn't write them. Okay. All right. So now verbally, tell me the other ones. If zinc is increased, which way? Shift left.
Decrease or
Decrease in the
the
driving force of the.
backwards or reverse?
Well, no. If you're decreasing the driving force of the forward reaction, reverse reaction, causing the voltage to decrease and the the E cell to decrease. Yeah. Talk to me. Okay.
Do you
Yeah.
want to change the ion?
Uh-huh. Because so far, yeah, so far we've only said concentrations in terms of concentration products or concentration reactants. We haven't said anything about the size of electrode, right? So does size matter in electrodes? No, not at all. Solids are irrelevant totally to this equilibrium. Therefore, their size cannot affect the equilibrium or the E cell. Note to self, this is your problem set. Size of electrodes do not matter. Concentrations matter. Okay. All right, next reaction. Determine the E cell for the previous system if the battery is 99.9% discharged. So this battery is almost dead. We've almost used up all of the reactants, right? So in the previous example, we had zinc plus copper 2 equilibrates to copper. I'm going to write this the other way because I have this first. Sorry, equilibrates to zinc 2 plus copper. Okay, so for this reaction, our reactants are being used up, right? What should happen to the reactants? They should start to disappear. They should be decreasing. But as they decrease, what happens to the products? They increase. So right now, in our new situation, 99% discharged, we have very little reactants, and we have a lot more products than what we started with. Our new equilibrium has too few reactants and too many products. Which way should it shift? What should happen to E cell? It should decrease. Okay, and I'll show you that, prove that to you now. Okay, so theoretically or logically, that should make sense. But before this reaction occurs, you know.
No.
Okay.
I was going to tell you 5 to 5.
Okay, 5%. Before the reaction occurs, we always start at standard conditions. We always start at 1 molar. Do I care? No. 1 molar here. Drug hair? Yeah. Sorry, that's your chemical for drug hair?
Nope.
No. Okay, solids don't matter. Before the reaction occurs, to start with 1 molar and 1 molar. That's a normal galvanic or normal cell. 99.9% of this has disappeared. So how much has disappeared?
0.99.
9. You know, and I'll put a 0 there just to make you happy. Okay, so this leaves us with 0.001 here. Not sure what that little dot is. There we go. On the other side, what I take away from the left, I add to the right. Adding 0.999. Here's my new conditions of zinc. So with this new situation, our new equilibrium would be favoring the production of more reactants, so it would be shifting left. But how do I prove that? My E cell of this initial reaction at standard conditions is 1.10 volts. This was our example that we had like very first in the lecture today. So this is at standard. So what would you expect it to be at non-standard here?
Higher than that.
We just said it was decreased, right? Because we had too few reactants and too many products. So
Oh, yeah.
give me a guess. 0.9. Okay, let's see. Or 0.10, we'll see. So my Nernst equation allows me to calculate. Oops. Minus 0.0592 over n log of q. All right, so what is, give me my q expression first. So q is equal to what over what?
Yeah. Okay.
Zinc, I know. I said sodium had a 2+ charge earlier. I haven't said that since like 5th grade. Okay. Okay, so here's zinc and copper. That's the only things we care about. Notice though that we have a 1 and a 1, so we have an exponent of 1 and 1. If this was not 2 electrons moved and 2 electrons gained, we would have to balance with coefficients, yeah? And then we would have exponents there. So that's going to be a problem later on. Kicking my stuff tray. Okay, so E cell is equal to that E naught, which is a standard, which is something you can calculate from a reduction table, minus 0.0592 over 2 moles of electrons gained and lost. So 2 is our net here. And log of what?
Isn't it 1?
1 point, Why do you think I did that before, during, and after? Oh, new initial conditions.
That's, yeah.
These are my new initial conditions. If it was 1, I wouldn't be doing the Nernst equation. The Nernst equation is only for calculating the new E cell after we have new conditions. New original conditions. Yeah, I'm sorry. Yeah, exactly, because it's going to shift back if it was possible to in a battery, which sometimes it's not. Okay, anyway. 0.001. So, dun, calculadora, 1.00 volts. And our theory was correct. We decreased our E cell due to the new conditions, having too many products and shifting back to the right. To the left. So they might ask you to give some quantitative decision or qualitative explanation. Most likely qualitative. But I need to know if this are your problem sets right now. Next one. Oh, this is just a quick reminder. You know that this right here was the equivalent of saying 0.0592 over n. Can't do it. Log of k, because this was at equilibrium. You don't really need to know that one though, so we just write that down. This one is the other one that we previously wrote, and this is another version of delta G. The two that are on your reference sheet are the delta G equals negative NFE and the negative RT ln K. So if you ever have to find heavy cell and you want to find delta G, you can. Or if you ever have delta G and you want to find K, you can this way. Just pretty much know where to find it in the reference sheet. Those are there for you. Okay? And then this is also another quick reminder. You don't have to write this down. If you want to, you can. This part right here, delta G is less than 1, which means it's negative. What's it mean? Spontaneous. E cell positive, spontaneous. This one right here is the one we haven't reviewed yet, but a very large K means that the products are favored So all of these, when we say spontaneous, we're assuming you mean spontaneous in the forward direction. Okay? So just remember those three things can relate. Other than that, you already know this stuff. Yeah. This is a reminder slide. I was going to pick it out, but it's there. Oh, I'm sorry. Awesome. Next one. Okay. Concentration cells. Okay, so a cell is just simply an anode and cathode, right? When I say concentration cell, I mean that the concentrations are different amongst the anode and the cathode, but it's exactly the same reaction. It's exactly the same, metal or ions present. So I can have a concentration cell of zinc and zinc 2+, where in the anode I have 0.1 molar, in the cathode I have 15 molar. They're the same half reactions, but different concentrations, you see? So what's the only driving force that's forcing them to actually react or let electrons flow? Just concentration, because there's no difference between the E of the cathode and the E of the anode, because they're the same dang thing, right? So when you minus the same from the same, what do you get? 0. So the E cell for this reaction is going to be 0 if they were the same concentrations. But the concentrations here are going to be driving the reaction to occur. So the things you need to know from this slide are, how does it flow? How do the electrons flow? We know they flow from the anode to the cathode. But you need to know that the less concentrated one is going to be considered the anode. And I'll tell you why. And the more concentrated is the cathode. The anode has less concentrated solution. It wants to eventually increase its concentration of solution, and the cathode eventually wants to decrease it because they want to get to equal concentrations, because then it will be at equilibrium. They have equal concentrations here because they are the same substance, so that's something we can do for it to become the equilibrium. At the anode, what do we draw on the electrode at the anode? A V or a beard? Do the V. What does that mean?
That it's losing mass.
And where's the mass going?
Into ions.
Into ions. Okay, so at the anode, the solid is converted to ions. What does that do for our concentration problem here? Increases the concentration. At the cathode, what do we draw?
The beard.
The beard. Okay, so what's happening here?
It's increasing of
Thank you.
electrode.
The ions are going to solid. What does that do to our concentration?
Lowers.
Decreases it. So eventually, the anode's going to increase its concentration, and the cathode's going to decrease, until they become equal. If they're equal, they're at equilibrium, and the E cell is 0. It's dead. The battery's dead. Okay, but right now, we're going to assume that they're not equilibrium yet. We're going to explain what happens, and then calculate the E cell of this original situation. Yeah?
So if the cathode and anode have the same concentration, the E cell is 0?
If they're the same concentration and they're the same elements. Okay. Everything's the same. That means there's no driving force anymore.
Oh.
If they're different electrodes, the driving force is their potential differences. If they're the same electrodes, the driving force is their concentration.
So in a concentration cell, I have different concentrations of the same element?
Yes.
Okay.
Example on the next slide. Okay, and this pretty much is exactly the same thing that I just said. But I like to draw pictures and arrows. You okay? Awesome. Okay. Here's my first example of nickel 2. And I'm assuming it's nickel 2 because nickel usually has a 2+ charge. All right, so help me draw my cell first. We haven't drawn a cell in a while.
Draw the little buckets.
Buckets. What's my anode and cathode?
Well, it's just nickel.
Nickel and nickel. Okay. Okay. What's down here?
The concentration.
I don't care about sulfate. Ah, okay. Same stuff, right? Okay. Now, what have I forgotten here? Salt bridge and concentration. Okay, electrons are flowing this way, right? Those are ugly electrons. Negative, positive. Okay. So, according to the information given, 0.001 molar and 1.0 molar, who is the anode? How do you know it's 0.001? Less concentrated one. In a concentration cell, the less concentrated solution is at the anode. You gotta know that, okay? So this one's 0.0010 molar, and this one's 100 molar. And I would, since this is not like, explicit, I'm going to say this is the anode chamber, and this is the cathode chamber. But, I mean, so like Dub is saying, low, usually the electrons going that way, we know. But just in case, electrons are going that way, losing electrons, gaining electrons. Sometimes you got to be like really explicit with the AP examiners because you don't want them to mistakenly say you were ignorant and didn't write something. It's just like, I mean, come on, we know the electrons are going that way. Okay, so what's happening at this electrode? Losing solid, depositing ions, okay? This one? Ions are depositing on the solid to make the beer. All right, let's write this in NIE form. So are you going to draw this one first? All right, so what's happening over here? Okay. Thank you. Ni solid, 2.
Plus 2 electrons.
Second one?
2 plus.
Okay, so we've exactly opposites, yeah?
Yes.
All right, so you didn't have to write like that. You could have gone straight to NIE. You know that there's nickel solid and there's nickel ion. Making, guess what? Solid and nickel ion. Okay. So, it's exactly the same thing, but I write this because it helps me figure out where does the concentration go in the Q. Okay, so I mean, I know this looks really stupid, but it does help you. This nickel 2 plus is going to nickel solid. So this nickel 2 plus is in the cathode or the anode?
That's the cathode.
How do you know it's the cathode?
Because it's.
Because what? It's a rig, and you know that nickel 2 goes to nickel solid in the cathode. So label it for yourself. This is the cathode one. The cathode one is 1.00 molar. The cathode one is in the reactants. This will go on the top or bottom of the fraction. Bottom. When you do products of reactants, this will go on the bottom. This one is nickel solid going to nickel ion, which is occurring in the anode, which is going to be the 0.001 molar. That will go in the products. Okay, question? Because when I write out the Q for this, Q is equal to nickel 2 over nickel 2, and I need to know which nickel 2 is which nickel 2, which is which nickel 2, which is, I need to know it. I don't want to know. Okay, so I need to know which of these ion concentrations is which of these ion concentrations. That's why you label it, so when you put your Q in, you say, oh, products, anode, oh, reactants, cathode. Okay, so I know where the Q's go. I mean, I know what goes in the Q. Let's calculate the E cell. How do I do that?
You do. Hold on. Okay. You can do log of point.
Hold on. Log of Q. All right, now, what do I know here?
Oh, you're not doing standard.
I have to know something else, though.
Yeah.
E naught cells what? 0, thank you. What?
I thought EMF was E naught cell, or is that just standard? Not standard.
And EMF means just E cell. It could be E cell or E naught cell. It's just talking about the electromagnetic force of that
So
reaction.
this question, you're trying to find like the experimental one, not standard.
Because this right here, we already know. We already talked about
This
it.
is at equilibrium.
So, well, it's not because it's at equilibrium. It's because this is literally nickel's reduction potential minus nickel's reduction potential. So this is E cell equals 0 minus 0.0592 over 2 moles of electrons, log of 0.001 over 1.00. Anybody? Give me a tell you. Point what? 088. Wow, that's tiny. Make a deduction for concentration cell voltage. Huh? It's not very effective. It would not be a good battery, right? Alright, so better batteries would be
More higher.
More different.
drastically different electrodes or reduction potentials, or metals that have different, electrodes that have different metals. This is going to be a multiple choice question. You need to know concentration cells yield low voltages. Okay? Concentration cells, which are just difference in their cells with different concentrations, yield low voltages. It's like I'm talking a different language today. All right, last one. Uno más. Okay, I gotta get my notes here. Okay. All right, can you guys write out? Okay, first let's predict. I like to predict what we do. If I usually start at standard and then all of a sudden I have iron 3 plus with 0.005 molar, what happens to E cell? Increases or decreases?
Depends on which. Well,
It doesn't depend. Why decreases, Lexi?
As the product, the reactants have a lower concentration than 1 molar, so it'll shift to the left.
Keep going.
And so the products will be greater concentration than the reactants, and so Q will be small. Wait, no.
I like this. Keep going. Q will be higher.
So that it'll change the E cell to a lower number.
Right, because you're doing E naught cell minus a higher number, which gives you a lower overall E cell. I like the mathematical first there. Okay, cool. So zinc plus iron 3 yields zinc 2 plus iron. Can you balance this in your head, or do you need half reactions? No ballparks. I need it.
It's going to be 2 iron, 3 plus, and it's going to 3 zinc, and then it's going to be 2 iron solid and 3 zinc plus.
Thank you. How do you know this?
I didn't know it in my head.
Yeah, give me some reasoning.
3, because you have to multiply the 3 plus by 2, and 2 plus by 3, so you can balance the electrons.
Thank you, balancing electrons. Okay, so zinc goes from zinc to zinc 2, lost 2 electrons. Iron went from 3 to 0, or change of 3 electrons. Electrons need to be equal, so you need to make an overall 6 exchange, 6 mole of electrons exchanged. So zinc has to be multiplied by 3 to make it 6. Iron has to be multiplied by 2 to make it 6. Yeah? You did that in your head. All right, so here's my coefficient one I was talking about earlier, where you're going to have to change the Q a little bit. Before the reaction begins, during and after. Before we begin, don't care. Iron starts off as 100 molar, zinc is 100 molar. What happens?
They subtract 0.0050 molar from the iron 3 plus. Right?
It says determine blah 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 when that is that.
Oh,
so minus X.
Not minus X, I know what X is.
Whatever.
Yeah, but I mean, you
What's X?
9.
Okay, so now, do not make this mistake. I'm saying I'm subtracting iron from iron, because this apparently is my limiting reagent. It's the only thing here. So technically what you're doing is you're minusing this amount in a 2 to 2 ratio, because I have 2 moles of iron, and dividing by, the coefficient that goes with the limiting reagent. Remember that ratio? So what's the ratio going to be over here?
3 over 2.
What is it? 3 over 2. The 2 goes on the bottom because we're referring to this 2 as the limiting reagent, and it always goes on the bottom. So over here, I'm going to add 0.995 in a 3 over 2 ratio, because I'm making 3 times as many zincs as I consume 2 irons. So I should be making more than 0.995, yeah? See mathematically how that makes sense?
Mm-hmm.
Okay, so this is going to be this number plus more than what I subtracted over here because they're mole ratio differences. This is 2 point, some number, 2.4925 molar. All right, plug and chug. Give me the E cell now. All right, what's E naught? Oh, let me tell you. I can tell you. E naught is the reduction one minus the oxidized one, which is 0.33 volts minus a minus 0.76, which is the zinc one, and this is the iron one. Zinc is equal to 1.5 volts. All right, so that's our standard condition. So 6 moles of electrons. Thank you. Watch the third. Zinc is a 3 coefficient over
0.005 squared.
Julio. because we talked about the balancing of electrons earlier. You have that total net or net moles of electrons transferred. It includes 2 ions, which is 3 to make them equal, so the common rates come in multiple. These come in multiple? It's 6. I'll put your stuff in for question. 1.3. But I think somebody from first period told me that, so could be wrong. But I'm gonna go with this. And our prediction was correct. We should left, right? I mean, correct?
Good matter.
Right. Huh? You know the Nernst equation. Okay? And problem set, all you need to do is 1 through 5 on the problem set, not 1 through 8. It's on the next page of the notes. It says, like, practice problems, Nernst equation, electrolytic. You're doing those 5. How much time do we have left? Did I? 22 minutes, more than I predicted. Okay, you have 22 minutes to do those 5 Nernst equation ones, and you have 2 more FRQs today, as I told you earlier. Okay? I recommend drawing any cells you can, because it will really help you figure out what's happening. On the AP exam, even if they don't ask you to draw, I recommend you draw your galvanic cell or electrolytic cell, because it will vastly diminish your confusion. Somebody. I gotta put that on the
I
goggles.
know, I saw that when
I was looking for what yellow is. She said yellow.
She's dead, so that doesn't
I know, I don't know. I gotta write that out.
Yeah, why does it say stead?
Some that means quick means sell now. Stop it. Yes.
Okay, so I realized FRQ thing, but I did the one thing up here for the
Did you?
web
I
quest.
didn't on the web.
Yeah, well, I changed it, and then so I think that that's what this means. So this changed all the values positive, and then I just like scratched all those out. So if you're
Oh yeah, your graphs will be slightly awkward.
because they look like this, like they looked like the same graph, like they both had 2 points on this line, and then they both had
But
like an
that's like an
exponential.
ln function
Wait,
versus
which
a log.
one's the problem set?
Right? Isn't that ln looks like that? The log looks like that.
Log.
Log looks like that.
Oh, I don't
ln
know.
looks like this. It's supposed to be a little bit more linear. But yeah, you know
Doesn't know
what?
where
You're
that
good,
is.
and I can understand it. We'll go like that.
Sure.
Yeah.
Yeah.
Oh,
Whiskers or something.
Boxes.
Okay, I was just gonna ask, are you gonna want my FRQ from last night? And you just want to take it, go back and get it. Well,
Work on that for now.
yeah, I know, I'm done.
I didn't turn them in yet. Don't turn them yet. Thank you. I forgot about that.
No, that's today. Annabelle. I don't have that escape from
If you have them, oh, let me stop videoing.